So today we're going to be learning about one-step equations, adding and subtracting. So if we remember, equations are when we have some kind of expression that has a left side and a right side. So this would be an equation, 6 equals 6. I have my left side and my right side. You can also tell when you have an equation because there's an equal sign. How it's going to be different today, though, is we are going to have a variable. So remember, a variable is a letter that stands for some number. We don't know what that number is. So we have to figure out, in this case, what would a equal? A plus 6 equals 16. So our focus today is we're going to solve one-step equations by creating a diagram. So we're making a model and checking to determine that the equation is true. For my class, please make sure you are checking. If you are not checking your work, even if you have the right answer, I'm going to make you redo it. So please make sure you are checking. It is important also that you show your work and that you have that diagram down. This is going to be a foundation for what you need to do in 7th grade, and you might look at the problems today and say they're really easy, but you need to be able to make that diagram, that model, and check your work because the problems are going to get harder, especially when you reach 7th grade next year. Alright, so I want you to remember this phrase. The right side must always equal the left side. So what that means is if I have this expression, 6 equals 6, my left side must always equal that right side. It doesn't make any sense if it doesn't equal the same. Does 7 equal 6? No, it doesn't. So that's why it always needs to equal that exact same thing. We're going to see why this is important with variables. Write it down. Remember that phrase by repeating it. Get a tattoo if you're really dedicated, but you probably won't want to. But you need to remember that the right side of an equation must always equal the left side, and vice versa. The left side must always equal that right side of an equation. So let's look at this example. If I have a plus 2 equals 6, I'm going to repeat this phrase because I remember it. The right side, so my right side 6 must equal the left side. Even though I don't know what a is, I know that a plus 2 equals 6 because my left side always equals that right side. Even though I don't know what a is, I know that these expressions are going to be equivalent or the same. Alright, so before we start with the modeling, we have to remember what tape diagrams are. So remember, tape diagram is just a rectangle that we use to model numbers. Larger rectangles represent larger numbers. So here we're just going to practice. I need a tape diagram of 6, it says. So I'm going to draw my tape diagram of 6. There's 6. I'm going to label it. And then I'm back to, I need to draw my tape diagram of 10. So I'm going to draw my tape diagram of 10. And it's going to be longer because I know 10 is larger than 6. So it's only going to make sense that this tape diagram is bigger than 6. Since 10 is bigger than 6, my picture needs to show that 10 is bigger than 6. So on to our next one. We have our phrase again right up in the top. The right side must always equal that left side. We're going to create a model and solve this expression. This a plus 2 equals 8. So first I need to make a tape diagram of that right side. So my right side again is this 8. So I need to draw a picture. I don't know how big 8 is, so I just make a item, a length, and I say that's 8. How big is my tape diagram? Well, I just know it's 8 because that's all there is on this right side. So I'm going to focus now on my next part. Here's our tape diagram that we just made. Now we need to make a model of the left side. So what's my left side again? Well, it's this a plus 2. I forgot. What's that expression I told you to remember? Oh, that's right. It's right down here. The right side must equal the left side. So I know my right side is 8. I know this left side is also going to equal 8. When I draw a picture, do you think the pictures need to be the same? Well, I think they do because I know my right side equals left, so I know my right side is 8, my left side is going to be the exact same thing. So I know if it's going to be the exact same thing, because they're equal, it's probably going to be the same length. And now, this is where it's going to be a little bit different. I see 8, but here I have 2 parts. I don't know what a plus 2 is if I'm looking at just 8, but I know the whole entire thing is a plus 2. I also know that 2 is less than 8, so I'm just going to break a piece off and say this is 2 right here, because I know 2 is less than 8, so I know it's going to be a smaller portion, which means this whole part's a over here because I have an a and I'm adding it to 2. So now I can look and I can figure out, oh, it looks like it's going to be a little bit simpler. Again, we already talked why it needs to be the exact same length, why it needs to be the same from here to here as it is from here to here. It's because they both equal the same thing. The right side equals the left. So now we can move on to figuring out what exactly is a. So here I have my tape diagram again. What can we surmise or guess about the value of a? Well, it's pretty easy. I know 2 plus something must equal 8 because I know my addition facts well. I know that 2 plus 6 equals 8. That's the only number a can equal, is 6. Let's look at this. What if I thought 2 plus 2, so a equals 2? I know 2 plus 2 equals 4. 4 doesn't equal 8. What if I pick a different number for a? I'm going to say I thought a for some reason was 5. 5 plus 2, well, that equals 7. Does 7 equal 8? It doesn't. So I see here that there's only one value for a, and that's 2 plus 6. So a has to be 6. So let's move on. This is my phrase. It's going to make it so we can solve a little easier. It's very similar to the one we had previously. The right side must be equal to the left side, only we've changed a little bit. So whatever you do to the left side, you must do to the right side. I'm going to explain it right now, but again, we need to remember it the best you can. Whatever you do to the left side, you must do to the right. Write it down, repeat it, get that tattoo again. Whatever helps you remember. So here we're going to use that phrase we just remembered. Whatever you do to the left side, you must do to the right. To solve it a little bit easier, I have my expression a plus 2 equals 8, and here I'm going to apply it. Whatever I do to the left side, I must do to the right. What I want to do is I want to do something called isolating the variable. Meaning I want this a all by itself. If this was all I had was a equals 6, you can look at that really easily and tell me, well, duh, a equals 6. But here I have some other numbers in here, so I need to isolate or get that a by itself so it's easy to read. And how I do that is I'm going to perform the inverse. Inverse means opposite. So you'll hear me say that word a lot. Inverse, and all that means is the opposite. So here's my original expression, a plus 2 equals 8. What's my opposite of addition? Well, I know the opposite of addition is subtraction, so I'm going to be subtracting, here's my subtraction, whatever my number is that's near the a. So here I'm going to be doing the inverse. Instead of adding 2, I'm going to subtract 2. And this is where this phrase comes in. Whatever I do to the left side, I must do to the right. But what I just do to this left side, I subtracted 2. So what I have to do is on my right side, I also have to subtract 2. That's my inverse when I do the opposite operation. And then I have a equals 6. Well, why is that? Well, what I can do is I can write it out. A plus 2 minus 2 equals 8 minus 2. 2 minus 2 is obviously 0, so I have a plus 0. I can rewrite that as a equals 8 minus 2. That is 6. So let's try one more. It's the same answer we got, that a equals 6, using algebraically, using that inverse, that math without the models. It's the same thing we got from that tape diagram. Let's try this one. We're not going to draw a tape diagram just to save us time, but I have a plus 3 equals 5. I'm going to look for the inverse. So what operation am I doing? Well, I'm doing addition. The opposite, the inverse of addition is subtraction. So I'm going to subtract. Whatever I do to the left, I must do to the right. So I'm going to subtract something from the right side as well. And what am I subtracting? Well, to get this a by itself, I need to subtract whatever number I see. So I'm going to be subtracting that 3 right there. Again, whatever I do to the left side, I must do to the right. So I'm subtracting 3 on the left, so I subtract 3 on the right. I'm left with, this is 0. This would be 2, so I'm left with a equals 2. We haven't got to that check part yet, and I told you we're not drawing a tape diagram, but that's all we're going to be focusing on for this part right here. So let's try one more problem. By checking. So here I know from my previous 2 problems that a equals 6. It's pretty obvious for us that a equals 6. So we're just going to try it something now. I'm going to check. My class, what does this say? Check. It doesn't say do whatever you want. It says check. So please make sure you're checking unless you for some reason want to do it over again. So how I check is I substitute. I take this value for my variable and I put it in for a. So I'm going to get rid of that variable and I put my number in. So I have 6 plus 2 equals 8, and I'm going to see, is that true? Does that make sense? Well, I know 6 plus 2 is 8, and I know 8, since my left side must equal the right side, 8 equals 8. I know my answer is correct because it checks out. So let's try another one. I have 3 parts: create a model and solve. Next, solve it algebraically. So remember, algebraically means using that math. And then I'm going to check my answer like we just did. So my first part is I'm going to look at my problem. B plus 9 equals 15. I'm going to create a model. So I'm going to start with my model. And I'm just going to draw, oops, I need to change my color. Oh, I know what it is. Here we go. I'm just going to use my pen. I know my problem is going to be equaling 15. So here's going to be my rectangle. I know the length is 15. Since I know that my left side must equal the right side, I know it's going to equal another length of 15. And how do I break this 15 up? Well, I know there's a 9, and I know there's a B. And so what do I do next? Well, I can now figure out, what does this B equal? I know that, oh, and look, it actually already kind of looks like what my answer is going to be. I know that 9 plus some number to equal 15, I know that's going to be a 6. So what does that mean? That means B equals 6. And if I'm unsure, I can look and, hey, look, they're the same length as well. I'm going to solve it algebraically. So again, using my math, using that inverse, I have B plus 9 equals 15. I'm going to do the inverse. So inverse means opposite. I see addition, so the opposite of addition is subtract. So I'm going to subtract. And then how much am I subtracting? Well, I see the number here is 9, so I'm going to subtract 9. Whatever I do to the left side, I must do to the right side. Then I'm left with B equals, this is 0. 9 take away 9 is 0. Then I have 15 minus 9, that's 6. So look, my answer checks here, 6 and 6, but that's not checking. Remember how we check, just to make sure, is I'm going to substitute my answer in. If you're checking your work, there should be no reason why you ever turn in a wrong answer with algebra if you are checking your work. It may take you a long time, but you should never turn in the wrong answer. So what does check my work mean? means I'm going to rewrite my problem. I take my variable answer and I substitute it in. So instead of writing b, I know that b should be 6. So I do 6 plus 9 equals 15. And then I just have to check. Does 6 plus 9, well, what does that equal? That equals 15. And does 15 equal 15? Yeah, they equal the same. So I know I checked my work. I know this is the right answer now. Let's try another one. Here I have 12 equals 8 plus c. So our other ones, we've been writing the answer, what we would normally call the answer, that single one right here, on the right side, but here I just wrote on the left. Remember, our commutative property of addition says I can flip them around. I can use that same idea and just flip the parts of my equation around if you want to make it look more familiar. Now I can begin. I know it's going to be a length of 12 because that's what it's telling me it will equal to. My left side equals the right. So I'm going to draw another fraction bar, so my left equals the right. I break it up into its two parts, an 8 and a c. And now I need to figure out 8 plus what number equals 12? Well, I'm going to draw my fraction bar again. I have 8, and then 8 plus what equals 12? Well, I know 8 plus 4 equals 12, and so there we go. There is a slight problem here. You might notice that this 4 looks almost the same size as this 8. Since we didn't know what my variable was to begin with, it's okay, since this is just my work. What is important, though, about this is I check it using my algebra, and I check it down here. If I get a different answer than this 4, then that probably means I made a mistake, and maybe the mistake was because I didn't make them the right sizes. But I'm just going to check with algebra first and see if that is even going to be a problem. So I'm going to do 8 plus c equals 12. I'm going to look. There's a problem here. I'm not adding a c, or I'm not adding or subtracting an 8. I'm adding or subtracting a c. So what do? Well, remember, 8, I'm doing its inverse. So what's the inverse? Again, that means it's opposite. So what's the opposite of 8? Well, if I remember, that's a negative 8. If I think of the number line with the positive and negatives, I have a positive 8 over here and a negative 8 over here. And I'm just going to do the inverse, being the opposite. And what do I notice when I have a negative 8? Or I notice that, it looks like a subtraction sign. So I'm going to just try that and see if I get the same answer, since a negative 8, the opposite, looks like a subtraction. So I'm going to have this will equal 0, 8 minus 8. I'd have c equals 12 minus 8. That equals 4. What do you notice here? They're the same. So I'm going to guess it's probably correct that I'd use that negative. So now I'm going to go down here. I'm just going to substitute my work in to check my answer. My problem was 12 equals 8 plus c. 4 is what c equals, so I'm going to rewrite it. 12 equals 8 plus, and then my 4, because that's what my c equals. And then 12 equals, what is 8 plus 4? That's 12. And look, my left side equals my right side. So I know my answer was correct. So my answer was, of course, c equals 12, or c equals 4. All right, let's go to our next one. And this next one's going to have something slightly different about it. So I want you paying careful attention. How can we show d minus 5 equals 7? Give it a try. Don't forget, we need to create a model, solve algebraically, and check your answer. Tell me if this seems correct. I'm going to start with a tape diagram because it should be 7. Then I'm going to break it up and I know it's going to be 2 parts. So here would be my D, and here would be my 5, because I see a D and a 5. Is that correct? Let's think about that. If I look at this, this would be 5 plus something equals 7. So this would be a 2, because 5 plus 2 equals 7. So I'm going to check my answer. D minus 5 equals 7. 2 minus 5 equals 7. Does 2 minus 5 equal 7? It doesn't. So I know there's a mistake somewhere in my work. So we're going to check on this little hint here. We have a harder time showing tape diagrams using subtraction. You'll notice this one's different because it has that subtraction in there. So this one's a little bit harder because of that subtraction. Remember, what we're trying to do when we're searching for answers using variables is, I don't actually care that D minus 5 equals 7. What I'm actually looking for is, what does D equal? So when I have a subtraction problem, what I do is I start out with D all by itself, because that's actually really what we're looking for. When I look back here, you'll notice that that's what I'm looking for in this problem. I'm actually looking for, what does C equal? And I'm looking for those equal lengths. So I'm going to be doing the same thing. I'm looking for, what does D equal? But now I have to do some flip-flopping. So D equals what? Well, I know that with my D right here, I'm taking away 5. So I'm taking away 5. So here I have my D minus 5 equals 7. And then I have my 5 on this side. So let's take a look at it again. I'm starting out with my whole D, this whole entire D, and it's saying I'm taking away 5. So that's where this part comes from. I have this D, and then I'm taking away 5. D, and there's this chunk of 5 that's being removed. Now, here's my other part. Well, Mr. Wimbley, how'd you get this D minus 5 equals 7? Isn't that just the same as saying it's taking away 5? Well, what I'm looking at is, I know what this whole part is up here. This D minus 5, I know that equals 7. So what I'm looking at down here is this 7 portion. Because D take away 5 is 7. Here I'm taking away just 5. Here I'm taking away D take away 5. I know it's going to be confusing, so when we do it algebraically, you're going to see how it looks much easier. But if you notice, once I simplify, I get rid of this D take away 5. I'm left with just that 7. I have 5 and 7. That 5 and 7 is this D up here. And so what is 5 plus 7? Well, that's 12. So let's check our answer algebraically. Since we're doing this one online, I'm going to have you guys just ignore this part over here. So for my previous example, I remember that D equals 12. Let's check it algebraically. Well, I have D minus 5 equals 7. I'm going to look and do the inverse. Here I see my subtraction. So what's the opposite of subtraction? Well, it's addition. So I'm going to be adding something. How much do I add? Well, I see the only number by my D is that 5. So I'm adding that 5. And whatever I do to the left, I do to the right. Then I'm left with D equals, this will be 0, 7 plus 5. That's 12. Does that check out? Yeah, it totally checks out. Is my problem done? No, because I need to do what? Check my answer. So how do I check my answer? Well, remember, I rewrite my problem. D minus 5 equals 7. And then I substitute, what does D equal? Well, it's 12 minus 5 equals 7. 12 minus 5, that's 7. Does 7 equal 7? Yeah, I think it does. So now we're ready to move on to our next problem. So here, if you were in our class, you'd be working with a partner, but what I want you to try is solve this one, or this one, or this one on a piece of paper. I want you to create a model, solve it algebraically, and check your answer. If it's not showing me your checked answer, your work where you checked what does your variable equal, you'll be redoing the whole thing. So pick one of these problems and then solve it using that model that we have on the previous ones, like right here, where you have that model, that algebra, and that checked work. I'll erase it for you so you can maybe pause it if you need to come look back at it, and then you can fast forward back to where those problems are, or however you would like to solve it. But you're using that model, solving it algebraically, and then showing me with your checked work. So pick one of those, give it a try. When you're done, turn it into the turn box and then go to the next part. So I'm going to have you pause your screen and then solve one of these, turn into the turn box, and then continue on with the lesson. Alright, so your last step, then I'm going to have you guys go to Socrative.com and give it a try on solving some of the multiple choice questions. If you pass, then I'll come over and let you go to math games. If you didn't pass, you're going to watch the whole video again, take the test again on Socrative, and then give it a try. So why do we need to use the inverse or opposite operation when we solve an equation? So I'm going to look for my keywords equation. So it's going to be something with a variable that has a left side and a right side. Why do I need to do the inverse? Well, I do the inverse because I'm trying to isolate the variable. I'm trying to make that variable all by itself. Because if it's all by itself, I can easily tell what y equals. Here, if it's not all by itself, like how I started my problem, I'm not quite sure what y is, especially if I use bigger numbers like y plus 124 equals 516. No idea what y equals. If y is all by itself, though, it's really easy. So I use the inverse to isolate the variable, to make it 0. So here, how do I make a positive 2 0? Well, I subtract 2. Then whatever I do to the left, I have to do to the right. So I have y equals 4. So one last time, how do I make the equation with an isolated variable, or why do I use the inverse? I use the inverse so I can get my variable all by itself by making everything else equal to 0 except that variable. Alright, your exit ticket. This is what the rest of the class will be doing. Since you're doing it on the computer, your exit ticket is Socrative. If you want to give these ones a try, go ahead. If not, and you're ready, head on over to MrWimbley.com. Click on our class links portion. And then you'll head to the math section for Socrative. So you're looking for that Socrative portion that says math, and that will give you your room number, the hyperlink, and the password. Good luck. Hope you pass your exit ticket, and I'll let you know if you can go to your math games if you passed it.